Start recording, and then press play from beginning. Hello, everybody. My name is Alfonso Landaverde. This is Lab O5, and we are going to, we could choose whatever topic we wanted. So I chose constant motion, revisited, because, we had a full semester. Go back to the beginning, right? Stuff like that. I don't know. Um, so the key physical concepts for constant motion of an object would be stuff like the position update formula, which would be like so. So if we know velocity is changing position over time, you can update it by doing r initial plus velocity times change in time equals r final, because you can redistribute the formula, right? Like change in r is rf minus ri. You multiply by t to both sides. You get v of t equals r final minus r initial, and then you just move our initial to the other side by adding it, and then boom, you get this formula. Pretty easy, but at the beginning I didn't know where it came from. I just remembered it, to be honest with you. But that's the key physical concept that you need to know for this one. Uh, some concepts for the experiment itself, because this is the video that we will be using. What do you mean you couldn't play it while I'm recording? Well, that's not fun. Let me see if I can do the glow or this version. Let me scroll through and then play. So the ball rolls through left to right. It only goes on the horizontal, the x-axis. So because of that, we can ignore the y-axis, and we can ignore all the forces that apply to that, like normal or anything like that. It's not fixed on a point, so you can't use angular momentum, any of that. Yeah, we can throw in new concepts that we can ignore. It's very simple, bare bones. Uh, and so now that's our video and our experimental video. And let's go ahead and show the graph for it. So here's the tracker model. It gives us all our positions. We can ignore the y because that's just human error of me clicking everywhere. But the x position, it shows constant motion, or roughly constant. The things that would make it not constant would be things like, I don't know, air resistance, curvature of the ground. I don't know, friction, stuff like that. But it's a lacrosse ball, so it should be mostly frictionless. It should be nearly identical with the experimental model, or the predicted model. And here's our predicted model. So all we had to do was grab the time at which the center of mass for the ball first enters the screen, because we kind of treat it like a point particle in this. At least that's how I treated it, because then you don't have to deal with mass or other things like that. It'll just cancel at the end of the day. It's a point moving. Um, so we just get that initial time, and the velocity just the velocity vector was calculated by taking when it leaves the screen, when it enters the screen, and averaging it. Because if we're assuming that it's constant motion, constant velocity, then we can just take the average velocity and run with it. And then this is our model. Roughly similar to the other one. X position ends at this, at that time. So let's go ahead and show if those are similar. Kind of. Close enough, honestly. Um, so now that we've gone through the predicted model and the experimental model, we can now come to some interesting thoughts. And this is our conclusion. So what could have caused some of the differences between the two? That would be, again, things like the human error, or glow script cutting me off at 23, so I don't get the final positions. Because if we notice these two, they both end at different times. Why would you do that? This ends at 0.90, so we kind of have to stop at 0.90 to get to see if they're the same position. And this one ends at, 1.04 e to the negative 3. This one ends at 0.843. So there's some differences in the velocity of the ball, at least as calculated, and that difference would be probably because the other one's taken at a lesser like frame rate. So basically, for it would make it appear as though this ball, the experimental one, went slower than this one, just because we took that average velocity. But when we transferred it to that one, it appears longer because this one runs for more time. Uh, and then with concepts that we've taken over the rest of the semester, we can very happily ignore them. This is an easy physics problem. Maybe it was easy from the beginning, but it's much easier now. And so those were my interesting thoughts. Thank you guys.